All right, we're going to get started on the last section of chapter 9. This is section 9.4. And in this section, we're going to be talking about quadratic congruences with composite moduli. As you recall, in the first three sections, 9.1 to 9.3, we talked about congruences or quadratic congruences and quadratic residue theory for odd primes. So we're going to extend this to actually any integer. So the objectives of this section is going to be, we're going to give first a necessary and sufficient condition or conditions for the solvability of the simple or reduced to quadratic x squared congruent to a mod powers of odd primes. Then we're going to work on powers of the prime 2 and 2 squared and so on. And then we're going to sort of combine 1 and 2 to give us a, the theory of quadratic congruences and the quadratic residue theory for any positive integer n. Throughout, we're going to be giving examples to illustrate the different ideas and the different methods of solving these different kinds of the quadratic congruences. So let's get started with the first one. And actually, we're going to start with the theorem and tell us under what conditions this x squared congruent to a mod, a power of odd prime is solvable. And also we're going to see that the proof tell us a method by which we could apply to solve. In other words, it's a constructive type of proof. All right, so this is first theorem, 9.11. And it reads like this, if E is an odd prime and A an integer relatively prime to P, then the congruence, the quadratic x squared congruent to a mod e to the alpha, where alpha is an integer bigger than or equal to 1, has a solution. If and only if x squared, actually let me write it in terms of Legendre simple, a p is equal to 1. And this in itself is equivalent to saying that x squared congruent to a mod p is solvable. So basically what this theorem is saying that if x squared congruent to a mod p is solvable, then x squared mod congruent to a mod any power of p is solvable as well. All right? So let's go ahead and start proving this. So let's go in this direction, assume that x squared congruent to a mod e to the alpha has solution. Let's say x sub z. So this implies and we have x sub 0 squared congruent to A mod p to the alpha whole. And this in itself implies p to the alpha divides x0 squared minus A, and which makes x0 squared minus A is a multiple or some k. Well, actually, we could use also properties of congruence is that if this congruence relation holds for an integer, it holds for any divisor of that integer. But if you want to go from scratch, you could do this, and this in itself y equals p times k p alpha minus 1. And this means that p divides, and again, this means that x0 squared is congruent to the mod. So we have the congruence holds for mod p, and from our previous work, this means that the Legendre simple is going to equal to 1 mod p, and this holds, of course, for the power of p. So that implies that A, B is equal to. So we are done in this direction. Let's go the other way. So we're going to go this way. So this, actually doing this way. All right. So here let's assume that the Legendre simple is equal to 1, and we wanted to show that the congruence x squared congruent to A mod p to the alpha that has a solution. All right, so we wanted to show x squared congruent to A mod p to the alpha as and really, this is where we're going to have a constructive way how to go from the solution from x squared congruent to A mod p to p squared and p to the third and so on, to a higher power, basically, of p. Now we're going to do this is by induction. On alpha. All right, here of course we have a solution for every alpha bigger than or equal to. So for alpha equal 1, of course, we obtain the original. For alpha equal 1, we have x squared equal to A on p. This has a solution since by assumption A by B is equal. So let's assume that the statement is true for assume that x squared congruent to A mod p to the k as solution for some k bigger than or equal to 1. And you want to, of course, show it is true for p to the power k plus 1. So this has a solution. Let's say x sub 0 is a solution to x squared congruent to A mod p to the. All right, well, let's use the definition. What does this mean? And try to obtain solution for k plus 1, p to the power k plus 1. So that one has a solution means b to the k divides x sub 0 squared minus a. And this in itself implies that x 0 squared can be written as b plus a b to the k. Or actually the other way around. Should be actually a for some integer. So once you translate this is into divisibility into an equation and shuffle things around, this is what you get. All right. So let's now consider the linear congruence equation, which is 2x sub 0 y is congruent to negative b or plus b if you wish, mod b. All right. So we have in here the greatest common divisor of, that we're starting with a and b is equal to 1. These are relatively prime. And since x 0 squared is congruent to a mod b, because the Lejeune simple for this is equal to 1. This implies that the greatest common divisor of x 0 squared and b is also equal to 1. One other thing, also the greatest common divisor with y is x 0 squared. And this in itself implies greatest common divisor 2x 0 squared p is equal to 1 because p is odd prime. Is odd. This means that this equation, all right, has a unique solution. This implies this linear congruence equation has a unique solution. All right. Let's call this unique solution y sub 0. Let's say y sub 0. So what we have in here, we have this itself implies 2x sub 0, y sub 0 is congruent to negative b mod p. This holds. All right, now the question, how are we going to use this information to come up with a solution for the quadratic x squared congruent to a mod p to the power of alpha plus 1, or k plus 1 rather. All right? All right, well, let's see what does, again, this, we can get to from this that p divides 2x sub 0, y sub 0 plus p. And this makes 2x sub 0, y sub 0 plus p is equal PR for some integer r. All right? All right, we're going to start putting things together. We're going to define a new number with x1 to be equal x sub 0 plus y sub 0 p to the k. All right? Then we're going to square both sides of this. And this implies that x1 squared is equal to x sub 0 plus y sub 0 p to the k squared. And this is equal x0 squared plus y's x0 y0 p to the k plus y0 squared p to the 2k. Now we're going to substitute for x sub 0 by this. We're going to substitute for this by this. We have x sub 0 is equal a plus b to p to the k. All right? So this becomes equal to all of this, a plus b, p to the k equals 2 x sub 0, y sub 0, e to the k, plus y sub 0 squared, equal to 2k. I think I'm going to do one more substitution. And first of all, we're going to combine these together. And we're going to have e plus, or let me put the 2 x0, y0 first, plus p to the k, plus y0 squared p. Now this quantity, remember, is equal PR. All right? So we're going to substitute that for PR, and this, the whole thing becomes A plus R p k plus 1 plus y sub 0 squared p to the k plus 1, k minus 1, and p k plus 1, like this. Okay? Now I'm going to take this as mod e to the k plus 1, so then these two terms cancel out, and so this becomes congruent to a mod p to the k plus 1. What does this mean? This means that this x1, all right, is a solution. So this implies x1 is equal to x sub 0, y sub 0, p k is a solution to x squared congruent to a mod p to the k plus 1. And then by math induction, this x squared congruent to a mod p to the alpha actually holds for any integer alpha. So finally, we have, therefore, by math induction, x squared mod p to the alpha has solution for every alpha bigger than 1. All right, so this completes actually the proof of the theorem. Now let's look at an example how we can find solution for powers of other problems. As I said, the proof indicates the way to find this. I'm just going to illustrate this with an example. Here's that. Let's find solutions, if any. Maybe we don't, if the condition is not satisfied, okay, that this is a sufficient condition, then it doesn't have solution, which is the Legendre simple being equal to 1. All right, so if any, for this equation, congruent to 23 mod 7 to the 6. The first step, all right, is actually, which is both, to consider this equation and determine its Legendre simple, or go ahead and 23 here, all right, or just solve. If it does have a solution, then the original equation is going to have a solution. Now for this, because 23 is congruent to 2 mod 7, give us a difference of 21. So this implies that we have this equation to do. And by trial and error, because it doesn't make a big difference, this has x sub 0, which is equal to, well, actually we could, again, find what is 2, 7 in here. This is minus 1. And remember, we have 7 squared minus 1 over 8. And this is minus 148 over 8. That is 6 even positive. So yes, it does have solution. This one has solution. Or as I said, you could actually write what the solution is. So x sub 0 is equal to 3 is a solution, which you can check. 9 minus 2 is 7. And the other solution, which is x0 prime, which is going to be 7 minus x sub 0, which is 4, is another incongruent solution. And this is it, because by Lagrange's theorem, this has at most 2 solutions, so in fact it has exactly 2 solutions. Now the question is how we can go from 7 to 7 squared. So we're going to go step by step. So to do this, we're going to consider, remember this, consider the linear congruence, which is 2 x sub 0 y congruent to negative b mod mod p, which is 7 in this case. This is the general, all right? Now, so we need to solve this, okay, or find what actually the b will be for this, okay? So this actually becomes where also we have to express, okay, where the x0 squared is equal to a plus p times p, and this one is 9, and the a is 2 here, okay, plus p, I don't know what it is, and p is 7. So the solution for this, for p is equal to negative 2, okay? We see it far out. This one is 9. Oh, this one is a 23, but this is the original one. All right. So this is 23, and this implies that b is equal to negative 2. Okay. Now, in this equation, it's going to look like 2 times 3, that will be 6. Y is congruent to 2 mod p. So I'm going to solve this to find y sub 0. In fact, we could reduce it dividing by, the p is 7 here, supposedly. Right? This is 7. All right, then we're going to solve this linear congruence, which we know that it should have a solution. So this 6y congruent to 2 on 7 is equivalent to 3y 1 on 7, and this y0 is actually equal to 5, is a solution, is the solution. For solution mod 7. Now we're going to go x1, which is equal to, remember, x sub 0 plus this 7 y sub 0, b y sub 0. In this case, this is going to be 3 plus 7 times 5. This is 38, is a solution to the square, to x squared congruent to 23 mod 7 squared. So this is one solution, and the other incongruent solution is obtained from this one, x1 prime, which is equal to 49 minus 23, which is equal to 11, is the other incongruent solution. Again, do x squared congruent to 23 mod 7 squared. Now we go and do 7 to the third using the same procedure. So we're going to start with using this x1. So this is the third step. Going to solve x squared congruent to 23 mod 7 to the third. Again, we have x0 or x1, actually this is what we call is equal 38 is a solution to x squared congruent to 23 mod 7 squared. So we're going to express this x1, which is 38, as a plus b squared. And in this case, the a is in 23. The b we need to determine, and this is 7 squared. So we need to solve basically this equation for b, and when you solve for b, this gives you 29. Then we consider the linear. Consider the linear congruence, which is 2 x sub 0 y is congruent to negative b, all right, mod 7. But no 7 squared here. Actually, we always use 7. This is in the induction that we have. All right, for this case, it's going to be 2x sub 0 y. We put all this together, becomes 76y is congruent to negative 29 mod 7. And you solve this, you find that give you y sub 0 is equal 1 is its solution. It's only one solution. Now from this, we want to go to the solution of the top equation. So we have x sub 2, which is equal to x sub 1. This is supposed to be x sub 1 in here, but this is x sub 1. All right, so this is x1, then we have y sub 0 times 7 squared is equal 38 plus 1 times 49. This is 87. Is a solution to x squared equal to 23 mod 7 to the fifth. All right, and in the other solution, and x2 prime, which is 7 to the third minus 87, which is equal to 256, is the other incongruent solution. Well, as we see, it is a systematic procedure. Could be very lengthy, of course, if we want to find much higher powers of certain primes or with bigger numbers. Now we're going to give a similar solvability criterion for powers of the even prime 2. So here's the second theorem, 9.12. All right, this is solvability of quadratic congruences for powers positive. Goes like this. Again, let A be an odd prime, an odd integer, sorry. In this case, to satisfy the condition of relatively prime, A need to be odd, all right? Then we have first part is x squared congruent to A mod 2. There's always a solution. The second is x squared congruent to A mod 4. 2 squared is equal to 4. There's a solution if and only if A is congruent to 1 mod 4. So the integer to be quadratic residue, it must be of this form. The third, x squared congruent to A mod 2 to the n for where for n bigger than or equal to 3. This again has solution if and only if A is congruent to 1 mod A. So these are the necessary sufficient condition for powers of 2 and powers of 2. Okay, let's start with the proof. have this one, x squared congruent to 2k plus 1. All right, and this is congruent to 1 mod 2. And this implies x equal 1 is a solution. But it would actually satisfy this, and this is the only solution. All right, there is no other solution because 0 is not the solution, and these are the two possible. All right, let's look at the second case, that is x squared congruent to a mod 4. Well, let's assume this one does have a solution, all right? X sub 0 is a solution. And we need to show the A must be of this form. So this implies x 0 squared is congruent to A mod 4. Holds. So this one actually does hold. And this implies that x 4 divides x sub 0 squared minus n. Now we know that any square of an integer is congruent to 1 mod 4. So this is back in chapter 4, which makes that the x sub 0 squared is going to be equal to 4k plus 1 for some k. Now let's look at this relation. 4 divides 4k plus 1 minus a. This implies that 4k plus 1 minus a is equal 4m. For some integer m. And solving for a near, we come up with 4k plus m plus 1. So this implies, yes, a is congruent to 1 mod 4. All right, so if it has a solution, it must have be congruent to 1 mod 4. Now let's go with the converse of this. Conversely, assume that A is congruent to 1 mod 4, and this makes A equal 4k plus 1. Now let's consider this congruence. Mod 4. This would be the same as x squared congruent to 4k plus 1 mod 4. And this is equivalent to x squared congruent to 1 mod 4. And this has two solutions. Has two solutions. x1 and x equal to 3. So 1 squared is 1, minus 1 gives you 0, and 9 minus 1 is 8, and that divisible by 4. All right, let's look at the higher powers of 2. Part C. Now you're going to consider x squared congruent to a mod 2 n, where n bigger than or equal to 3. Again, we have the x squared. Square of any integer, any odd integer rather, this one, in this case A is congruent to 1 mod 8. So in other words, for this to be solvable, so therefore x squared congruent to a mod 2 to the n is solvable if this condition is satisfied, if a is congruent to 1 mod. So this takes care of the condition being necessary. All right? Now let's assume the other way around. That A is congruent to 1 mod 8, and we wanted to show x squared congruent to a mod 2 to the n bigger than or equal to 3 is solved. How we're going to do this is again by induction. On n. So for n equal to 3, the initial value, we have x squared congruent to a mod 2 to the third this is actually is solvable. Because of this, we have a solvable because a is equal. It is of this form. We are assuming a plus 1. And the congruence becomes x squared congruent to 8k plus 1. And this is congruent to 1 mod 8. And the solutions for this, which is also this x equals 7, is a solution. And actually also, let's see if there's another solution in, and 1, okay, 1 and 7, okay, and x equals is a solution. X equals 1 and 7, these are the two solutions. All right, so in other words, this is solvable. Now let's assume that it's true for n, and go for n plus 1. So we're going to assume that x squared congruent to a mod 2 to the n as solution for some n bigger than or equal. Remember a of the form 8k plus 1. So we are under this assumption. All right, well, So what does this mean? This means that, again, let's say solution, as a solution, let's say x sub 0. So this means that the 2 to the n will be dividing by x sub 0 squared minus n. This whole. And which make here we could write that x0 squared is equal a plus b times 2 to the n for some b an integer in C. Similarly, we're going to consider a linear congruence. So we have going to consider the linear congruence equation, which is x sub 0 y congruent to, again, negative b mod. We have the since a is odd and x0 squared is congruent to a mod 2. This implies that x0 squared is odd. And x sub 0 is also odd. Which makes the greatest common divisor for this one. So this means that the greatest common divisor of x sub 0 2 is equal to 1. And this means that this equation has solution. And it is unique. Sort of similar to the same procedure as we did in the previous theorem. We're going to call this solution y sub 0. And we're going to see how this solution leads to a solution for 2 to the power mod 2 to the power n plus. Kind of similar, at least similar procedure, but probably different in the execution. All right, so let's have this. So this going to define or let x sub 1 is equal this x sub 0 plus y sub 0 multiplied by 2 to the power n minus 1. I want to write this as a claim that this, then x1 is a solution to this. Mod 2 to the n plus 1. Okay, so make this as a claim. We're going to do some similar sort of calculations to make this satisfy this. This x1 satisfy the second line equation. So the same thing in here, we're going to square this. Both sides. And this becomes x1 squared is equal sub 0 plus y sub 0 to n minus 1 squared. And this is equal x0 squared plus 2 x sub 0 y sub 0 to the n minus 1 plus y sub 0 squared to n minus 1. Similarly, we're going to substitute for x sub 0. This one we have it as was A plus B multiplied by 2 to the n. We have that in here. So this is equal to A plus B 2 to the n. This one, we're going to substitute for the x sub 0, y sub 0. The 2 and this one, so this becomes x sub 0, y sub 0, 2 to the n, plus y sub 0 squared 2 to 2n minus 2. All right, let's actually take these together in here. Combine these together so we could replace this from the solution of the linear congruence equation. So this one is A plus 2 to the n. We have B plus x sub 0, y sub 0 plus y sub 0 squared. And let me write this as 2, actually, n plus 1 times 2n minus, it's going to be minus 3, okay? And remember, because n is bigger than or equal to 3, the last exponent of 2 is going to be, bigger than or equal to 0, so that will be fine. All right, now we're going to replace, we're almost there. So this implies that x1 squared, which is equal A plus 2 to the n, and I'm going to replace the B plus x sub 0, y sub 0. This is equal to 2r. Remember that this coming from, probably I did not write this, this is because we have, for this, we have the x sub 0, y sub 0, we have a dissolution mod 2. So this holds, which means that we could write 2 divides x sub 0, y sub 0 plus b, and this gives me that. All right, so we're going to substitute for this, and then we have also in here the y sub 0 squared 2 to the n minus 3. Actually, this need to be, this is to the n, all right. And then we have, so we need to have, there is another 2, and then this one 2 and plus 1. All right, one more equality, and then we're going to take mod 2 to the power n plus 1. There's one more equality in here. So this is equal A plus 2n plus 1. So we're going to combine these together. R and y square 2n minus 3, 2n plus 1. Now, this is congruent only just to A mod 2 to the power n plus 1. Of course, here we need the plus 1. So this is as 2 to the n plus 1, 2 to the n. So when we do mod 2n plus 1, it becomes 0, and this is it. So therefore, x1 is a solution to x squared congruent to a mod 2 to the n plus 1. Then by math induction, x squared congruent to a mod 2 to the n as solution for every n bigger than or equal to. So if A has the form 8k plus 1, this has a solution for every power of 2 bigger than or equal to 3. All right. Our next objective is actually to consider any integer. And I'm going to do it slightly different than the way the book does it. To start with, I'm going to state the theorem that's true for any actually polynomial congruence, because this is true for every polynomial. All right, at least as far as the how to solve. All right. So I want to have this next theorem. I want to call this theorem star. I'm going to be referring back to it. That goes like this. If n is a product of n sub i's, I equal 1 up to r, where the greatest common divisor of any two of these is equal to 1 for every I does not equal to j, between 1 and r. So these are relatively prime, so these need not be prime themselves. So that's a little more general, in other words. All right? Then the solution set of the polynomial congruence f of x, without even specifying what it is quadratic, congruent to 0 mod n, is the same as the solution set of the system of congruence equations which is this: f of x congruent to 0 mod n1, f of x congruent to 0 mod n2, and so on. And f of x congruent to 0 mod n sub. So this is what this theorem is saying. Let's kind of look at it. So we have this congruence equation that's mod n, which this one is composite, could be any, basically any integer. What this is saying that to solve this is equivalent basically to solving simpler equations. F of x is congruent to 0 mod each one of the factors of n. And later on, and that actually this is the theorem, last theorem, which is stated in the book, we're going to take n to be, this is the prime factorization. So, and then we know the conditions under which it is solvable. The proof of this is actually simpler, easier than doing it for the quadratic, because we use this notation f of x, save us writing square or anything like that. All right, and let's see how this actually works. Very simple proof. So the solution set for both the one single congruence equation is the same as the solution for the system. That's all what it is that this theorem is saying. All right, here's the proof. So let's assume that x sub 0 is a solution to f of x congruent to 0 mod n. So in other words, this belongs to the solution set of this. And I want to show that this one is also a solution for the system. So this implies that f of x sub 0 congruent to 0 mod n holds. All right? And this implies in itself that n divides f of x sub 0. This holds. We also know that n sub I divides n for every I. So let's put these together. We have ni divides n, and n divides f of x sub 0. This implies that ni divides f of x sub 0 for every I, using a transitive property of divide. And this in itself is equivalent to f of x sub 0 congruent to 0 mod n sub I. And this is true again for every I, which means that x sub 0 is a solution to each equation in the system to the system. The system being that f of x is congruent to 0, 1, n1, n2, and so on. All right? Now, let's go to the other, which means that the solution set, therefore, solution set of f of x congruent to 0 mod n is a subset of the solution set of the system. Now I'm going to go the other way around, and suppose we have a solution for the system, and how we can find the solution for the single equation. Now let's assume that x sub 0 is a solution to the system. So this implies that f of x sub 0 is congruent to 0 mod n sub I, or every I between 1 and I. Now, since this one holds, all right? Now, since these n sub i's sub j are relatively prime, or every I does not equal j, by the properties of congruences, we have f of x sub 0 is congruent to 0 mod 0 prime. So it's supposed to be the least common multiple, but least common multiple is going to be just n. All right? So this implies that f of x sub 0 mod n, both of these hold. And this means that x sub 0 is a solution to the single solution to the single congruence. Congruent to 0 mod. All right. Now the question which remains unanswered is how we can find the solution for just this congruence, the single congruence, using our knowledge about solutions for the components or the factors of n, which means that the system itself. Because what we have discussed, we know how to find a solution for powers of primes, odd or the even, and we know a necessary and sufficient condition when we are solvable. Now the question is solving, knowing, having that knowledge, how we can build it, how we can use it to solve f of x congruent to 0 to any composite. Okay, and that is what we need to discuss next. And guess what? We're going to be using, of course, the Chinese remainder theorem. All right? So this is the procedure of how to go from a system of equations to solving a single congruent equation. I want to start actually with an example, and then I will give the general procedure. All right? All right, so here it is. Let's consider this example. We're going to solve this single equation. And I want to actually have it in general, not even just this, the reduced one, which we could do in, later on. So our f of x in here, which is x squared plus 3x plus. And again, the idea is we say that the solution set of this, okay, so that by the theorem of the star says that solution set of f of x congruent to 0 mod 6 is the same as solution set of this system, f of x congruent to 0 mod 2, which are the two factors of 6, and f of x congruent to 0 mod 3. Now, this system of congruence equation is not the linear one. It is not like what the Chinese remainder theorem tells us. But we can, of course, solve this by the methods that we learned for primes, in this case is 2. The solution for this actually, this has just one solution, unique solution, x equal to 0. And we can do this one by trial and error, okay? Because you could actually reduce this, even this one, which is x squared plus 3x plus 2 congruent to 0 mod 3. This is very simple, okay? You can take the 2 out and it becomes x squared plus x, this one, or you just try the 0 and 1. And this is equivalent to x squared plus 2 congruent to 0 mod 3. And the number that satisfies this is x equal 1. 1 plus 2 is 3. And x equal to 2. All right, so we have one solution here and two solutions there. Now, this is what we need to use the Chinese remainder theorem to find the solution for the system. Means value of x that satisfy both if the first f of x congruent to 2 and f of x congruent to 3. Now we apply the Chinese remainder theorem to all combination of solutions from the first one, the second one, if there's a third one, a fourth one, and so on, like this. So we're going to take x congruent to 0 mod 2 with x congruent to 1 mod 3. So this is one system. And then we're going to consider 0 with 2. Of course, if we have the first system has two solutions, then we're going to have 2 with 2, 4 systems that we need to apply the Chinese remainder to. And then we're going to also look at this, x congruent to 0 mod 2, and x congruent to 2 mod 3. So we're going to apply the Chinese remainder theorem to these two systems. And so you need to go back to chapter 4 to recall how to solve to apply the Chinese remainder theorem to solve this. And the solution we get is mod 6. Okay, so for the first one, the solution you get is, let me see if I could actually, this one in here, the solution for the first one, let's see here. So these are the solutions that actually we get. I don't have the specific solution for these. Let me write the general solution that we get in here. Actually, I was wrong on the first one. Sorry. This x squared plus the 3x, we go back here. 0 mod 2. I always say this had one solution. In fact, it had these two solutions because this is equivalent to x squared plus x, and then 2 is 0 mod 2. And this has x equals 0, x equals 1. So we have 4 systems that we need to consider. So 0 with 1, 0 with 2, and then I need 1 with 1, and then we have another 2 system, 1 mod 2 with 1 mod 3, and x congruent to 1 mod 2, and x congruent to 2 mod 3. Yeah, all together, this one gives us a solution x equal, I think, 4, I hope I put these in the right order. This is mod 6. This one gives me 2. Let me see if I can. Yeah, this one is 2, mod 6. And this one is 1. Mod 6. Yeah, it's not very hard to see this one works for 1. And this is x equals 5. So then the solution for solutions to x squared plus 3x plus 2 congruent to 0 mod 6 are these numbers. And all these are incongruent. All right, 4, 2, 1, and 5. Which you can check them by substitution and reducing mod 6. So to give the general procedure, all right, to what this example actually, what we have used in this example, the procedure to solve okay, so in general, let's consider the system of congruences f of x congruent to 0 mod n1, f of x congruent to 0 mod n2, and so on. F of x is congruent to 0 mod n sub r. So we solve this, we solve each equation in the system. Because this is actually step number 1. Step number 2, let's assume that I don't know how I'm gonna write this one. Let me see it here. Let's say that assume that x1, x2, up to xr is one of the solutions. Is one of the solutions for the equations in the system respectively. Means x1 is for the first equation in the system, x2 for the second, so on. There might be more than one solution, okay? All right, so assume this one, then we apply the Chinese remainder theorem to find a common solution using one of these solutions. Common solution x sub 0 mod n by solving this system. X is congruent to x1 mod n1. So we're going to apply the Chinese remainder theorem to this system, to this simpler system. x2 mod n2 and up to x congruent to x sub r mod n sub r. So each solution for the system, we combine it together to come up with a common solution. And then we're going to consider all possibilities. Okay, so we're going to look at an example again to show how this is done. All right, and this would be how we would go about solving congruence equations with composite moduli. All right, let me do that, and then we're going to state the last theorem, basically, which is we already proved it for the quadratic. All right, so this is give one actually let me write the actually, I just want to just say what, the theorem. I don't want to write it down because it's RPC. Actually, let me write it. Don't want to repeat myself too many times in here. This is the last theorem, sort of summarizes the first two theorems together with the theorem double stop. Okay? And in it here it says this, and then let n be the prime factorization. K sub 0, E1, K1 up to P sub R, K to the power R, be the prime factorization of n, an integer bigger than 1. Then we have now we're going to let a be an integer relatively prime to n. Then x squared. Okay. Now we have this is a sufficient condition in here in terms of Lejeune symbol. Okay. All right. Mod n. This is solvable if and only if first the A Lejeune symbol A with any of the prime factors is equal to 1. This is for R equal 1, for I, sorry, I equal 1 to up to R. And for the powers of 2, we want A congruent to 1 mod 4. If 4 happens to divide n, but 8 does not divide n. And A to be congruent to 1 mod 8 if 8 divides it. Or we could write this in terms of congruences. All right? Now this covers actually basically the 4 because they have to satisfy. With 2, we don't need to because always it has solution. All right? Now, the remaining, so this gives us the necessary sufficient condition. Now the second part, it tells us how to solve, all right, this theorem. So if these conditions are satisfied, so this is the second part of this theorem, all right, if conditions A and B are satisfied, the solution solution set of x squared congruent to A mod n is obtained by solving each equation in the system, which is x squared congruent to a mod 2 to the power of k sub 0, x squared congruent to a mod P1 K1. Now we know each one of these in itself is going to be another reduction, a mod P R K for R. So this one, and apply the Chinese remainder theorem to find the common solution. And apply the Chinese remainder theorem to obtain solution, a common solution. Mod n. Actually, it is easier just to see through this one with the example I'm just going to present next. This is also what we applied it to a simple, the previous also example looks the same, and then I'm going to look at a longer example. All right. Of course, if these conditions are not satisfied, then the congruence equation has no solution, and we don't need to go through all this torture. All right. So whenever that's a solution, it's a problem, right? It's like those question in application form which says that if yes, then explain. If no, you don't need to. So you choose no, right? Okay. I present a couple of examples. I don't want to go through all the details of the solution, but hopefully there will be enough details for you to fill in if you are interested in going to the end of it. All right, here's the first example. And here we're going to concentrate on, again, quadratic. So we're going to take x squared congruent to 2 mod 190. First of all, 119, it's a composite, and this is equal 7 multiplied by 70. So the 2 prime factors of 190. So what we have to do to solve this, and fortunately these are, single, only the first power of 2 primes. Then we need to look at x squared congruent to 2 mod 7 and see if this is solvable or not. You can do it by trial and error, or you can do 2 7. And you can do this 7 squared minus 1 over 2, and this happens to be equal 1. Right? So this means this has a solution, and then we're going to look at x squared congruent to 2 mod 7. And again, calculate the Dijon simple for this, which is in this case 17 squared minus 1 over, this is over 8, I'm sorry. This is over 8, not 2, over 8. And again, you find this one. So this means that these equations, they satisfy this condition B. And because I don't have any, power of 2 in 119. Which means that, yes, this equation has a solution that satisfies those 2 conditions. And now the question is how to solve. So we're going to solve the first one. So the first one, the solution for this. Let me call this is 1 and this is 2. R. Yeah, this is the part which I'm not going to be, actually doing it here. So we get 3 and negative 3. And solution to 2 are 6 and negative 6. Again, you could, if you wish, use a positive solution, means take the negative 6 to one positive number is congruent to mod 17, and the same thing with the 7. Now, this means that we're going to apply the Chinese remainder theorem for 4 systems, which is take x equal to 3 with the second 2 and negative 3 with the second 2. And good luck, because that's going to take the whole exam time to finish. So then we apply the Chinese remainder theorem to x congruent to 3 mod 7 and x congruent to 6 mod 17. And then we're going to consider x congruent to 3 mod 7 and x congruent to negative 6 mod 17, and so on. And the last one, you go with x congruent to negative 3 mod 7 and x congruent to negative 6 mod 7. So there are 4 systems. So each one of these is going to give you a solution, all right, mod 190. So this one, with the magic of writing down, what I have is this give you negative 11, I hope, mod 119. And then the next one, it's going to be negative. Actually, in here I have some, these are written not in the same order. This one is 440, let me see here. Okay, I got the first one is negative 11. The second one is going to be 11 here. And this one, I'm going to leave the other one for you. As you can tell, this one is 3 negative 6. This one gave 45. And then there's the other 2 in between, or other. Actually, one more, 1, 2. Yeah, the third one in here, which is congruent to negative 3 and 6. X, this is mod 2, this is mod 77, so 7, and this is 17. The solution for this happens to be negative 45. All right, mod 19. So put these together, all these are the different solutions. So plus minus 11, plus minus 45. Let me give you one other example, and again, I'm not going to put the details of this because that's going to take to the weekend. And today is Monday, by the way. Next weekend, all right? But to try to give you the why computers are important, okay? They are better than our brains, right? Or why we are invented computers. Let's look at this example. X squared plus 5x plus 66 congruent to 0 mod. And I'm not going to write this even as, to multiply it out. It's 360, okay, which is 2 to the third, 3 squared times 5. So this is a 360. Okay? solve it. I give you a hint. This does have a solution, unfortunately, because it, to satisfy the condition, the A and the B condition. So to solve it, if I call this is f of x, to make my life easier, we need to start with solving mod 2. Actually, the fifth one, this one you could do by trial and error. You don't need to go 2 squared, and 2 to the third, almost nothing. Okay, so you can solve this by substitution. But then we're going to solve this one. Well, again, probably you could do substitution because these are small still. But if these are, big, this is a big prime with a larger, exponent. What you need to do is to solve f of x congruent to 0 mod 3. Then you want to do mod 3 squared, the procedure that we've done earlier at the very beginning. And then you're going to solve also this. This is a single prime. And then once you find the x's for this, the x's for this, and the x's for this, this is where the Chinese remainder theorem is going to come back again. And it turns out, after you do all of this, or wherever I got this from, that the solution for this one is x equal actually 1 and 2. The solution of this, fortunately, because this is a quadratic, so at most it's going to have 2 solutions, 1 and 3. And the solution set for this turns out to be 2 and 3. So when you combine these for the Chinese remainder theorem, you're going to have 8 systems to apply a Chinese remainder theorem. All right? And that's a whole lot, right? Okay, so this is it for chapter 9. This is the end of it. Initially, I thought of doing chapter 10. Then last night I was looking at chapter 10. I think I'm going to have a hard time even asking you questions from chapter 10. It doesn't have any kind of theory. It's a sort of a fun chapter to read, and it has to deal with cryptography, all right? But, as a material for a regular class, online especially, it is not feasible to, cover that material. So what I'm going to do is select some topics from chapters 11, 12, I think, or maybe 13, that would, constitute like the same thing, about 4 sections from different topics. Among these, I'm going to be doing, which integers can be written as a sum of 2 squares, which integers can be written as a sum of 3 squares, 4 squares, and then we're going to talk about Pythagorean triples, all right, and some what's called Mersenne numbers and perfect numbers. At least this is the initial plan. I hope we'll have the time to do these nice and fun topics as well. All right. So I'm going to stop right here for this lecture.